que você quiser, pode soltar. Bom dia a todos, prazer estar aqui com vocês. Vou começar essa introdução em português. Mais um seminário PESC está acontecendo. Hoje a gente conta com a grata e tem a honra de ter a presença do professor Davide Taibi, colega cientista bastante renomado e com atividades bastante intensa na área de arquitetura, inteligência artificial. Tá? O professor Taibi vai apresentar a palestra em torno de 50 minutos, 45, 50 minutos, e ao final a gente vai abrir para as questões. A audiência que nos assiste no YouTube, né, no nosso canal, por favor, participem do chat, mandem as perguntas que eu vou estar acompanhando e terei prazer em fazer as perguntas aqui para vocês. So, good morning, everyone. It's my pleasure to introduce to you Professor Davide Taibi from the University of Oulu, a full professor from the university that's been working a long time in software architecture and in artificial intelligence and all this stuff that mystifying our lives today. Professor Taibi is a very active participant of the ICERN, the International Software Engineering Research Network. We've been working together in this network for some time, and it's really an honor to have him here today to share some of his findings, knowledge, and new perspectives in the software engineering research and then empirical software engineering, artificial intelligence, cloud, software, whatever you want. So welcome, please.
Obrigado.
You are on the stage.
Obrigado. Bom dia a todos. So, yeah, my Portuguese is pretty limited. I understand, but not that much. So thanks a lot for the invitation. Today, I'm going to give you a kind of overview of our research, and in particular on how cloud is slowly evolving and how universities and how research is trying to keep up with the evolution of these cloud technologies. But let me give you a little bit introduction of me. As you can hear from my accent, I'm not from Finland. I live in Finland, but I'm not from Finland. So let's say my career started, there is... Sorry. Yes. No worries. You can't see the slides?
Yep. Here, I have to full screen.
Can you see? Can you see it now?
Yeah.
No worries. So I was saying, let's say I started from Italy and then slowly went up north to progress my career. I got associate professor in south of Finland, full professor in north of Finland. Someone say that if in future I want to become like rector, I need to go on the other side of the world because there is no human being north. Yeah, there is Lapland, but there's no that. I need to go way north. By the way, that's my research group. I just wanted to say that whatever I'm saying now is not my research, but it's the results of the research of the people working together with me. And we are now at the moment 12 people working in my lab. I give you a brief overview before starting on what are the research topics of my lab, before going in deep into the cloud aspects. So on one side, we work on modernization of legacy systems. So we want to try to understand how to make a new system modern? How can we improve systems that are really, really hard to modify? So think about those very old banking systems developed with COBOL, with the legacy technologies, or think about those systems that are impossible to modify anymore. So we give suggestions to the companies on how to move up to a new technology that will be useful for future 10, 15, or 20 years. Of course, it's not just about giving suggestions, but it's also understanding how to decompose a system. System is like a big monster. We want to divide into several subsystems, completely independent. So it's more understanding how to cut, how to compose all of them. And finally, after we give the suggestion of the possible architectural solution, we need to measure, because it's easy to move, but it's really hard to understand if you move for a reason or if you get an improvement or not. So we develop some metrics for measuring the quality of the architecture, measuring the quality of the software after the migration to cloud. And last, once you move to the cloud, you need to run your software, right? So you need to run it, so you need to operate it. And we are developing some algorithms and some approaches for orchestrating and operating the different systems, cloud-based system, on edge devices. And I will go also into this edge part. Finally, we have some legacy topic that is still having some good tractions. I was talking with Guilherme this morning, and we say, usually our research is really hard to get traction in industry. What we are doing is has a limited impact on industry, and that's true. And I was thinking exactly the same of this. This was my PhD topic back in 2010. I was doing something about software quality of open source software, try to understand how the open source community is evolving, try to understand how open source software can survive, what is the expectancy of the community. It was cool in 2006, 2010, but then died. After 10 years, 2020, 22, something like that, I start getting company knocking at my door, asking contracts and say, oh yeah, we saw your original research 10 years ago. It seems it's now time to put it in practice. Cool. So it's maturated. So never think that what you're doing is useless. Think that it might take traction. And I'm getting plenty of money to pay my guys in my lab. I have actually 2 people full-time in my lab, thanks to the consultancy project of this very, very legacy. Not doing any research anymore, just applying it. But this was just to tell you, don't think about what you're doing now can be useful. You don't see the application, can be useful in several years. Now, let's move to the core of the topic today. First, I want to give you a very brief overview of the evolution of software architecture in the last 50 or 70 years. So we started around the 1950, 1960, 70 with those old-fashioned monolithic architecture. So they were big systems developed all together, deployed all together in the same machine, in the same server. And whenever you modify a component, you have to be sure that all the other components are not, in fact, affected or impacting. So there is a decoupling. So if I want to change this tiny gear here, I need to probably adapt everything around. And this was a problem, especially when the software was getting bigger, bigger, and bigger. So what do they invent? They decided to decouple, so separate, slice, separate individual systems. And they invented this service-oriented computing. That's this one. That is, let's say, traditional. It has independent services. But what was the problem? At the beginning, it seems it was fine. This was around 2000, 2003, 2005. There was this connector in between that is called message enterprise service bus. That it was really hard to develop. And every time you modify something here, this gear was tightly connected with all the other gears. So that means the business logic was in the enterprise service bus. It was too complex. So people around 2010 started to think about a new modernization. And they say, okay, let's move to something lightweight. So the problem is in the message bus. Okay, let's move the logic to the nodes. So let's move the logic to the different services. And they propose microservices. Someone say Microservice is still service-oriented architectures, just done properly. Someone says something else, depends who you are listening. It's just a different taxonomy. By the way, they are different individual services connected with a very lightweight message bus, who is just sharing messages. There is no logic in the message bus, it's just sharing messages. And this allows, of course, to completely develop independently from the other services. Now, this is easy from the architectural point of view, for the structure of the code and for the organization. But the problem was the increased size of the system and increased size of the development teams. So let me give you a metaphor about food. Guillermo is having fun because I'm a kind of food lover, he knows. I need to find the metaphor with Brazilian food. I'll challenge myself now. Exactly. Yes, yeah. So usually the monolithic, it was the architecture of a monolithic system was like a plate of spaghetti. So no structure, all together. Now, I'm not saying that a plate of spaghetti is bad. I mean, I'm pretty sure if you try my carbonara pasta, you will start crying. I mean, it's amazing. But it doesn't, of course, I mean, just tell me when you're available, I'll be happy. But the problem is that there's no structure. And now, for microservice, we say the problem is the size of team. Now, the metaphor is, I want to serve a catering for a wedding of 1,000 persons. Imagine I want to serve 1,000 persons with carbonara. There's a problem with carbonara, need to be eaten in 3 minutes. After 5 minutes, need to be thrown away and need to make a new one because there is egg, fresh egg that dries immediately. So you can't wait. So if you want to serve 1,000 people in a wedding, you can't serve only 5 people now, 5 people then. You take 3 days to serve them all. And you can't have a pan as big for 1,000 people because you need to have this jumping in the pan. So it's impossible. It doesn't scale. So that's the problem. You can have multiple, what are you doing to scale? Well, you have multiple chefs with multiple kitchen, but it's hard. It's impossible. That's why they don't serve this type of pasta to the weddings. So what did they invented in 2000 with the SOA, the idea, service-oriented architecture? Imagine the concept of the pizza, but a huge pizza, one of those Guinness record pizza, let's say a 10-meter size pizza. So they ask different bakeries. So every team, every bakery can bake their own huge slice of pizza. Let's say the oven is like 1 meter by 1 meter. They make 1 by 1 meter slice of pizza. And then when the catering or when the wedding starts, wedding lunch or dinner starts, every team, so every individual bakery just arrived there, they put their slice of pizza and they recreate the whole pizza. When the pizza is ready, those huge Guinness record pizza is ready, everybody can start eating with a nice beginning of the dinner. But still, what's the problem? You need to wait that every team finish their task. So that's service-oriented architecture. Every service needs to finish the execution, so you can't have it ready. You can't start immediately. Microservices can fit pretty well the metaphor of finger food or small pastries. So that means you can easily ask an army of different bakeries or development teams to develop their own product, their own service. So someone will develop some food, someone will develop something else, someone will develop, I don't know, poutine, for example. You know, I'm a big lover of poutine. I mean, twice a day I got it for the last 10 days. I hope today I can get one. Yes. I hope. By the way, in that way, imagine if you get just 10% of the food ready at the same time. Well, you can still start the dinner. Not everybody needs to have maybe 20 pieces of finger food, all of them ready exactly at the same moment. It's enough to have maybe just one now, and maybe the other one in 2 minutes, and the other one in 10 minutes. So that's the metaphor of microservice. Every team can work independently, but when you talk about scaling, both in terms of teams and in terms of performance, we can have independent deployment. We can have independent also loading from performance point of view. So the independency here is boosted at the maximum speed. Now there is the new concept of function as a service that is like extremely highly decoupled. It's a different concept. It's like imagining you have just a function that develops only the whipped cream, the other one just the cherry, and the other one just the part below. It's hard to stand up the metaphor now from this point of view. But it's yet the new concept that is now introducing. And Nowadays, so back to this timeline, we say microservice 2010, 2020 we had serverless, 2022, around 22, we started to have micro front ends. So they say the front end was becoming too fat, so let's split the front end also into individual piece of front ends. That's same of microservice, but also splitting the front ends, easy. We had service meshes now in 2023, around that time, and people say you need to split the system into independent services as microservice, but also the databases. But some company didn't manage to do it, and now they had to invent a system to overcome this problem. And last year, we started to have the end of this big loop. Companies are coming back to monolithic because most of companies, or several companies, they realized that they moved to microservice for marketing reasons, because it was fancy, because the competitors did it, so if the competitors did it, I have to do it too. And they realized that microservice is way expensive, way more expensive than monolithic, and if it is not justified by a very large amount of teams and a very large amount of requests, it doesn't make sense. So it makes sense in certain conditions, but not in every conditions. So there are companies who are now going back to monolithic. Amazon Prime Video, for example, used to be completely microservice. Now half of them is officially back to monolith. Istio is also back. There are several, InVision, there are several who are back. So what I wanted to say is that every technology has a specific advantage in a specific moment or in a specific context. This is the example of microservices, for example. So let's think about productivity and complexity. So if I increase the complexity of my system, for example, in terms of number of features, if the complexity is really low, well, it's way more productive to develop a monolithic system because it's tiny. You don't have moving parts. You don't need to configure a lot of stuff together. You don't need to configure, for example, like a Kubernetes, different containers, different message buses to connect them together. It's just a software all together deployed in the same place. After the number of features or the complexity grows, well, the productivity of monolith at a certain point will get down because it's really hard to develop if you are too many people. And the productivity of microservice will remain pretty stable. It will get down when it becomes a huge monster. But at a certain point, there will be way big difference. Obviously, this is a theoretic diagram. We don't know where is this crossing point. So forget about those economics. When you study economics, demand and offer, try to find the cross. No, this is just in theory. We can't find it in reality, in software. But this was just to tell that whenever company adopt a new technology, they need to think about benefits in the future, both from the technical and from the economical point of view. So whenever we do the consultancy to the company, we try to let them understand. They say, yes, I want this, whatever is new technology. Well, does it make sense in the long run? Or where do you expect to be in 5 years or in 2 years? Do you expect to be here in 5 years? Okay, then let's consider maybe next year or in 2 years to make the change. You expect to be here in 6 months. Okay, let's immediately decide which of the two technologies you have. So depending on what's your expectance, you might have a difference. Okay, now that I give you kind of introduction of cloud technologies, I want to give you the introduction of what is our research group, what we call demystification process. So how we try to demystify the different hypes in software engineering. So first, whenever there is a new technology, first thing we do is a set of surveys with companies. We go to practitioner conferences, we talk with practitioners, and we try to understand why they are using a specific or that technology that we're interested on. Are you using it because of your competitors, because you have a specific benefit, and what are the benefits that you actually had? We did it in several contexts, and we realized that most of the time they were expecting to have a benefit, but they had a completely different benefit. We did it for microservices. They were expecting to reduce cost, but instead the result is that the cost was higher from 20 to 30% at least, but they had better independent team working together. So if your goal was to save money, well, then you are failing. So it depends what's your goal. And that's the point. We try to understand the benefit. When the technologies start to take traction, then we try to understand, again, with surveys and case studies, patterns and anti-patterns. So how to use this technology and how not to use these technologies in specific contexts. We do some follow-up case studies, of course. We do plenty of research works on that whenever the technology takes traction. And when the technology is stable and widely adopted, we develop assessment framework. So to decide to help companies understanding when is suitable and when is not suitable. And we did that for microservices. We were actually the first one writing something on process motivation and issues for the migration. We did that for serverless computing. We did that for micro frontends. Now we did it for cognitive and continuum cloud. And we are slowly doing it for whenever there is new technologies. Some people are always asking, how do you spot these new technologies? I love to follow at least one or two practitioner conferences every year. Usually I go to the practitioner conference, I try to go there and listen what are the hypes, or even without going, you just look at the presentation that they're doing. You can check the presentation, you can check the timeline, the schedule, you see the title, you see what is appearing more frequently, and then after that, you decide. And moving to pattern and anti-pattern, that was the same. We started for microservices. Actually, our catalog is the first one who developed the microservice bad smells. And we did the same for serverless. We've not yet done for micro frontends because it's not yet mainstream. So it doesn't make sense. I mean, it doesn't make sense to tell people how to do it if we don't have enough in the industry that can report benefit and can report, let's say, best practice and bad practices. And there is a very nice typo. Technology assessment framework is the last, they'll say the end of this path. And we did it only for microservices because it doesn't make sense to make it for the others. So now the microservices are stable, so we can tell the people when is reasonable to use microservice or not with a simple flow diagram. And let's say what I really love to show is my favorite example on blockchain. It's not mine, but I really love the way they develop. I try to publish 20 times something similar to that. No reviewer liked it, so we didn't do it. But this is what someone managed to publish on blockchain, non-peer review. I don't know why peer review doesn't fly. You should sell something like that. But it's really easy. You know, that's the idea. You start, can a traditional database meet your needs? Yes, no. If yes, you don't need a blockchain. I mean, and that's the idea. Can, no. Then does more than one participant need to be able to update the data? No, you don't need a blockchain. That's my dream flow diagram for technology. And we develop it for the company. This is what we did for the company, but it's not peer review because, again, you know, it's hard to get this through whatever type of publication. So the problem is not only to move. Okay, we do the migration. We try to develop properly. We try to develop in a clean and nice way without anti-patterns, following the, let's say, a nice decision. But in a long term, everything will degrade. So there is no system that will remain nice and clean. It's like humans. Slowly, it ages because you add features, you violate architectural choices because you keep on fixing bugs, adding features, and what was your very nice architecture that you designed 10 years ago? It's not the same now. It looks like an ugly monster, so it really, really looks pretty bad. I guess if you see some company, if you saw any company, yeah, it's very, 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 very common. So the question is your architecture changed in compared to what was the original definition? It's impossible that the answer is no, because it is normal. So how are we solving this problem? We are going to do something like back in the 90s, reverse engineering. You remember those reverse engineering rational rows, reconstructing Java code, but we do on the cloud side. So we simply do one level of abstraction over. We don't go at the code level, but we go at the service level. And how we do it? Statically, from the source code, and dynamically, evaluating the execution, the log traces of the system. Now, have you ever seen this car for Google Maps? Yeah. What are they doing? They're simply mapping statically the streets around the world. So there is someone who is driving this car, and the camera is taking all the possible streets, connections, traffic lights, everything that is around statically. So that means the system is not running. So in the end, this will create the map of the city with all the possible streets of the system. And what we are doing with static analysis is the same. We have some cars who are actually screening all the software, so actually parsing all the software and recreating the abstract syntax tree or the structure of the whole system. In the end, everything is going to be a kind of call graph. So it's similar to a Google Maps of the software. And we can do it from several sources. We can do it from the source code, from the infrastructure as a code, from the Git log, so activities, including also social interaction between the people, co-changes, from the issue trackers. We can do it from every point of view. But that's not enough. I mean, tools, unfortunately, are 19, plenty of them, but they're just from research. There are no tools from industry that do static analysis reconstruction. Our opinion is that it is too complex, and there are too many languages involved. So it's not easy to create a tool that is able to parse every language and keep it updated, because, you know, language evolves, so you need to evolve all your parser, maybe for like 20, 30 languages. It's really, really expensive. Let's move to the dynamic analysis. So dynamic analysis in Google Maps. So whenever you have a phone with Google Maps, you are sending your position to Google. So you are actually sending your traces of where you are directly to Google server. So Google knows where you are. Those four guys are telling Google where they are. And of course, this guy doesn't know, for example. And the result of that is that you can create the traffic. So you can have, for example, a street traffic view where you see the most congested route. And you can also see the bicycle traffic route with the most congested and most used. So in that way, with Google Maps and Google Traffic, you can see, so the city hall, for example, can take this info and see which streets are more used, at what time of the day. So do they need to increase the size of a street? Of course, here we're thinking about the city. So this is Manhattan. I'm pretty sure that they cannot, let's say, duplicate the size of this road. They need to take some other action. But in a software, you can do it. In a software, you can duplicate, you can replicate, you can put a load balancer, you can add more capacity for that point of view. So for the dynamic analysis, there are tools, and those tools are commercial. So there are plenty, like 10 commercial and 8 research-based. And they already reconstructed the call graph. What are the problems of those tools? Well, they reconstruct, but they don't tell you anything else. They just visualize. And I think this is a very big shortfall, where at least my research group would like to bring in the results of the research, because you're visualizing, but you don't tell if it is good, if it is bad. You don't tell anything. You just show, and without giving any type of information. So the potential for software quality analysis is really, really, really high. But I told you, we have the call graph. So what can we do that? Is it useful? Any idea? What can we do for call graph?
See where the heat maps of also, like which circuits is getting more requests to make the duplication after something like that.
Yeah, that's an interesting analysis at runtime.
We can also track back to the release process. If the behavior of a system changes, you can track back to the code request, the code development.
Yeah.
The original process.
Yeah, if you know how the system is structured, of course, you can track back. So what we propose is to do exactly what we mentioned in the beginning, so analyzing the quality. So from the call graph, you can analyze the anti-patterns. So we develop those tools to analyze the patterns directly here. This is an example of cyclic dependency. So you can see the red nodes they are the one involved with cyclic dependencies. But in our tool, we can detect like 12 or 13 microservice anti-patterns. And well, you can detect a lot of information on top of metrics. So everybody's talking about coupling. Have you heard about this coupling concept? So coupling is the idea on how one team is connected with the other team. So whenever I make a change, this other team needs to make a change. Or whenever my service needs to run, it needs to get info from the other service every single time. So this is type of coupling. And we develop 3 different type of coupling. Actually, we extended from existing coupling from monolithic systems. So at the moment, nobody were able to measure coupling. So we are trying to sell this in industry also. Structural coupling, so how the calls between services are actually running. And this is an example that you see that these red lines show that there is a strong amount of calls between these 2 services at run times. Or when it's red, it means every time I run this service, I also need to run that other service. So question is, does it make sense to have them separated, or should I keep them together? Cognitive coupling is about co-changes between services. So whenever I change one service, I'm changing also the other service. So there is not a direct coupling at runtime, but there is an issue still. So if I forget to make the change on the other service, then something will not work. And then we have the organizational structure coupling. So how the organization is structured and how the system is structured, following what was called this old Conway's law. So structure of the organization should mirror the structure of the system or the architecture of the system. And we did several analyses on that. So this is an example on how the structural coupling is evolved in several systems. And you see different colors highlighting how much. As you can see here, it's getting better and better in this system. This is an academic-based system. This kind of toy system that resemble a real system, but it's not a real system. But it just shows you graphically how it is evolving. When we talk about this organizational versus architecture, as I was saying, Conway's law say that the organizational structure should reflect the architectural of the software. So the dream would be to have the black team with the green team, the red team working on the black, the green, and the red service. The reality is not that. This is an example from a real software. The reality is that everybody's working and collaborating with each other. It can be nice saying that you collaborate, but it's not nice because every time you make a change, you got a problem. You need to wait that the other team make the change for you, or you need to ask the colleague, please fix that because I cannot deploy. I need to wait that you make this change before my deployment. So in our research, we developed this method to track back how the coupling is evolving, try to give some suggestion. And of course, the goal that we are doing is to identify mismatches and to give recommendation. So the ultimate goal, let's say the peak of the pyramid of our research is to tell the teams these 2 services have a problem. You need to decide, either you move some people from one team to the other to reduce the coupling. So if they keep on touching something else, they can move on the other team, or you move part of the code from one service to the other one, or you merge the two different services, or you make one service in between. I mean, we provide those options, and then we talk with the software architects, and we help them to reason. So based on the coupling and based on the patterns and the anti-pattern. That's the final part. So we are doing this architecture reconstruction also in edge domain and in what we call the 6G, sixth generation telecommunication software. You know, there was the 3G phones, 4G phones, 5G phones. In 2030, we're going to have 6G. That is just an extremely distributed platform, but it's not very different from edge computing. And once you run it, then we have the problem also of those orchestration, of loading. So it's yet another level of runtime that can be still visualized with call graph, but requires some algorithm to optimize it. And here we have in our lab, we developed this set of facilities where we provide a benchmark to the students to develop new algorithm. So we have a set of different edge devices. We have Raspberry, we have Jetson Nano, we had some basic computing, some clusters, and we have plenty of sensors. So there are like 10 cameras monitoring the people around. Here there is like, this is like a balance board. You know the balance board? It's like piece of wood, like a skateboard with a ball under that is completely unstable. And the guys are playing some tricks like skateboard tricks. So usually we give the master students this option to develop algorithm, the computer vision guys. They can develop some algorithm for doing whatever they want. One student, they develop this to monitor or give some ranking on the tricks, how cool are the tricks for this skateboard. Someone developed the one for the posture. So it tells me I'm seated the whole day like this, so stand it up. And there is like a vibration motor under the desk that vibrates and tells you you are sitting in a bad posture. It's like brr, brr, brr. Now we bought these bus shakers. Have you ever seen those bus shakers? They're like big motors, like 5 kilos motors that you can install under your chair. These are meant usually for simulating, for video gaming, for car driving video games, for aircraft. It can give you like a big bump, a big bump. You can really jump you on the chair. And the kids, they want to develop something for fun and give you a huge feedback when you do something really bad. The idea is that we want to produce an environment, an edge-based environment where our students and our PhD guys, they can develop a new system, new algorithm, and try those orchestration and those deployment systems directly on a real infrastructure. We don't care of what they are developing. We just do care that they are pushing the computation as much as possible so that the others, they need to do the part. So to close this talk, I cannot end a talk without talking about generative AI, right? The question is, will generative AI clean up the code, or will keep the code architected as originally, let's say, required by the software architects? Will it refactor? I mean, the dream that some people have, I mean, Valentina is still dreaming about the Roomba of software. You know, Roomba, those tool that cleans up the house. Valentina, my colleague, she says, I mean, if Roomba can clean up the dust, not everything, why we can't have a Roomba for software that clean up the dust, let's say the basic and simple things? Of course, I mean, if there is a chair, but I think the metaphor stands very well. If there is a chair in between, Roomba will turn around. So if you make something really bad in the software, those Roomba of the code cannot clean up. And my question is, can generative AI do this cleanup? Valentina is working at the code level. I'm working on the architectural level. So can we have a huge Roomba that can clean up also big things, or they can even rearrange the software? We still don't know. So in conclusion, we know we have plenty of technologies coming on the market. There will be continuously new technologies. Every few years, there will be a big revolution. People are now rolling back to microservice. So it's like a wheel that is slowly turning. We know that there is not the perfect solution. There is not one silver bullet. You can't say, I want to use like microservice in 2010 because everybody was doing it. It's going to be a mistake. You need to use what's needed. And I believe we as researchers, we can give our contribution helping companies understanding what makes sense to use in which context and what probably is just marketing or is not suitable for them. Still, it is possible. I mean, if you live in here in Rio, it is possible to buy, for example, a huge car. But imagine if you need to park in a tiny space and you have only a huge car. You can do it, but it's not the best option. I mean, depends on what is your requirement. And then we need to think about those economical issues, because the software architect can give nice and shiny idea, but if economically it's not feasible, need to think about it twice, and think about what are your problems before migrating or before adopting a technology. So if you are adopting a technology just because you think it will solve your problem, that will not solve your problem. If you have I don't know, economical problem in your company, it's not using a microservice or micro front ends that will change it. If you want to save money, it will cost more. You need to use a technology for what it is meant, and not just because it's fancy or it is trendy in that part. So that was all. Thanks for attending the seminar. And
Thank you.
Questions?
It's a very nice talk. So we have time for questions. It's open for questions for the audience. Please just introduce yourself and then
Thank you.
ask the question.
Hey, I'm Natasha. I'm from astrophysics, but that's another topic. I was wondering, what is the most expensive factor of microservices?
Well, the development is the most expensive because you have a lot of moving parts. So you need to connect different services together, and maintaining it is very expensive. A lot of companies are moving back because to develop and operate microservice is expensive, especially because you need to run on top of an infrastructure like Kubernetes. Kubernetes is very hard to manage. I mean, it's not hard, it's expensive. So you need to have persons who are dedicated to that. So if you are a huge company, it doesn't really matter. Let's say 1-2 person dedicated to Kubernetes. If you have like 1,000 developers, you can do it. But if you have 15 developers, you can't afford to dedicate 2 out of 15 just to manage that. So in that case, the problem is, again, operation and development for those extra costs.
Hi, my name is Bill. I'm doing master's in PESC, and my question is kind of similar to Natasha. I was wondering about the cost, because part of the cost of maintaining a cloud infrastructure is the cloud services, so AWS or Oracle or whatever. And does like having on-premises, even though on-premises you have to have people to care about the infrastructure itself that you really is passing through the cloud provider. But even though is it feasible, is it better to have like on-premises cloud instead of using a cloud service?
Yeah, this is a complex question that requires, in theory, a very long answer. In practice, it really depends on the people that you have in your company, and it depends on the resources. And also on the non-functional requirements. So if you really need something that has an extremely high response rate, very fast response rate, then you go on-premise. But it's not for cost aspect, because usually on-prem, it's worth just if you have an extremely huge system. If you have a medium small system, it's cheaper on the cloud. It's worth when you start spending 2 million euros per year of cloud, 1.5 million. But we know a lot of companies that they say up to €1 million per year of euros or dollars, more or less are the same, per year, still worth staying on cloud. Except if you have some privacy reasons or whatever reason that you need to keep it on-prem.
Hi, I'm Juliana. I'm also a master's student here. I have a mask on.
Yeah, no worry.
I was wondering, you were saying about your team developed a analysis tool.
Yeah.
You called it Prof.
Yes.
Is it? But Prof is the name that you gave, or is it you using
it's the name. No, it's the name that they gave to the tool. I mean, it has. I don't remember now. It's an acronym for the complete name of the tool, but yeah, it's the name that we gave to the tool.
Okay, but it's the same name as the Meta version, ProMeta.
Yeah. In fact, we should change it. Yeah. It's a different story.
I was wondering if it was Meta.
No. In fact, I mean, we should change it probably to avoid mismatch.
But we can talk later. But I was wondering how does it work? Like, what do you do?
What?
You use that dynamic for the name?
No, static. Prophet is only static. So what we are doing is to analyze the source code, and we look for every calls to external services. So, for example, we parse line by line every single code. And at the moment, we do it for Java, C# and C++ only. The accuracy is decent for Java and for C#, C++, not that much. Decent, I mean 80%. The problem is that you can call a service in so many ways, sometimes even indirectly. So it's not easy to catch when you are calling an external service from a static analysis. But yeah, that's what we are doing. Reading line by line and try to find any possible call to external service, or when you call a service through the message bus, when you're sending a message, so producing, and on the other side, when we have a service, it's the consumer who is reading your message.
It's easier when people containerize main components, isn't it?
Yeah. Well, it's easy, especially because if you containerize like in Docker, then you have the Docker image name, or you have the service name. So you are looking for that service name. It's much faster. But sometimes developers invent some very fancy tricks to call, because they say, yeah, it's more elegant, but then it's harder to spot. Yeah. Welcome.
More questions? Just now that the talk finished in the StreamYard, so I will give them 30 seconds to raise the hands. But I have a question. It's much more philosophical than applied.
Yeah.
Do you? Go.
My name is Arthur. I'm also doing a master's here. And how do you feel the impact of your work and similar works on actually demystifying the hypes for companies over microservices or blockchain?
Yeah.
All this matters.
Well, the point is that there are more and more companies who are now starting to use microservices anti-patterns. And I mean, I'm pretty happy that now companies knows what are the anti-patterns. Actually, if you look in AWS and in Azure, most of the anti-pattern that they mention is what we defined a few years ago. So they don't even link to us, but the name are those. I'm really happy. It doesn't matter. I mean, I don't need the credit. I need that at least my research is useful to the industry. And then the other thing is that, I mean, this is merely economic, you understand, but I need to maintain my research team and give them salaries. So through those kind of new ideas and new stuff, we got a lot of consultancy from company. So it's like a double side. On one side, we get the money for the consultancy. On the other one, doing the consultancy will help us to be close to industry, understand what they're doing, understand their problems, and then try to develop new methods, new technologies to, let's say, to improve the state of the art. Here, I'm not showing all the works that we are doing in between the demystification. There is a lot of works in between.
And also, as you see here in Swiss, I'm doing experimental software engineering with Jagati,
yeah.
And you're also from experimental software
yeah.
engineering. So you mentioned a lot about the code and dynamic and static analysis,
yeah.
but do you do with companies or projects analyze using experimental, segregate one team or one service to be a base analysis and keep going as they are right now, and another one to transfer part of the system as a monolith?
Well, yes and no. We do it most of the time when we do the migration. For example, we are not using an experimental software engineering process in the migration. In the migration, we simply try to understand what makes sense to migrate first from a pure marketing point of view and economical point of view. We do a lot of empirical software engineering, like doing A/B testing for example, developing new technologies or adopting new technologies. Or in some cases, for example, we do experiments or sometimes case studies to understand if some of those anti-patterns are really useful or not useful, if they bring return in terms of productivity or return in terms of quality of the whole system, software readability, and so on and so forth. So we use empirical software engineering mainly to validate those anti-patterns, and also this framework. The framework, of course, is the peak of the iceberg on a huge empirical process that probably lasted like 10 years.
Okay, I will skip my question because I have a question from the audience there. Some people, congratulating about the talk. A guy from Unesp, it's the São Paulo State, that's also enjoyed the class, the talk.
Thank you.
And we have a concrete question from Nabson Pava. He is a master's student, at the Federal University of Amazon, the
Oh,
other
yeah.
side of the country. And he's asked if your lab or your research group is still researching about micro front ends.
Yeah. We are working a lot. At the moment, we are still trying to investigate when it makes sense to use micro front ends, because there is a big problem that there is a very big difference between when using or when not using. So in our previous studies, it seems that only very, very large teams can use micro front ends. Otherwise, it doesn't make sense from economical point of view. But nowadays, there are also a lot of small teams who started to use micro front ends to rearrange their architecture. Now, we are trying to understand if it really makes sense or if they are doing it just for a marketing reason, or what are the benefits that they can encounter from this point of view. After that, of course, we will move to pattern anti-pattern if they take traction. But yes, I would say if you're interested in collaborating on micro front ends, drop me an email or directly go through Guilherme. Just put in contact with me.
Good.
Thank you.
And then I will be back to my question, because we can close that. Cohen's law, is it a conjecture or a law?
This is just a philosophical point.
I told you.
Yeah, I would consider more a conjecture. I mean, you can't consider as a law. It's not
quite complicated
strict.
to observe that thing.
And you cannot have a perfect respect of this Conway's law.
Yeah.
You can optimize in that direction, but the perfect doesn't exist. It exists only if you have two totally separated systems.
Yes.
Developed maybe by different companies, then it is.
Yeah. Cool.
But it's probably more expensive to have. I think every extreme is problematic. So if you want the extreme Conway's law, so perfection is going to be hard. And on the other side, the extreme mass is also a problem. Something in between, more toward those Conway's direction is better.
It sounds like an organizational suggestion.
Yes.
You have a feeling that things will be organized in that way.
From our point of view, what we are trying to optimize is to reduce the need of code changes and reduce the need of having a lock before deploying. So I don't want that a team need to wait the other team before deploying. That's the concept. Then if you have some coupling, but you are completely free to deploy when you want. You are completely free to call the different service without waiting. So the blockers are my problem. If there are no blockers, then it's kind of
very
acceptable.
Good. So let's call. No questions. Lunchtime. Thank you.
Thank you.
Very nice to have you here.
Thanks a lot for attending.
Very good. Thank you so much.
Thank you.
Well, nice. Really.
Thanks a lot for attending the seminar.